times 10 to the negative 3 set over 6.9 times 10 to the negative 4 is pretty darn close to 2. You don't have to slide decimals. I'm just offering that as maybe perhaps an easier way to look at these numbers. If your mind can think small decimals, great. I like to think in terms of numbers I can visualize. So I would consider this as 7 and 14, or close to 0.7 and 1.4. But if I doubled the concentration, I clearly see the rate doubled as well. It's first order with respect to iodide, 0 order with respect to hydrogen. We read this as rate is equal to K times the concentration of H2O2 raised to the first power. Iodide is to the first power, and hydrogen with no effect, power of 0. Let's talk more about this rate constant called K. K is a constant, and it actually has units associated with it. We can solve for K by just taking one of the trials and plugging in what we know. Once we have the rate law, I usually just select the first trial only because it's written first. The rate of 6.9 times 10 to the negative 4th molarity per minute is set equal to K, what I'm solving for, times the concentration of the peroxide times the concentration of the iodide. Both are raised to the first power, and the hydrogen, of course, just dropped out. I can solve for the value of K in the following way. From trial 1, but this is interesting. Since K is a constant, we indeed should get the same number no matter what trial I use. So rate from trial 1, 6.9, E negative 7, divided by 0.1, divided again by 0.1, and we get a value where K is 6.9 times 10 to the negative 5th. Let's think about units. What we have is a little formula to help us calculate this. The K units are found by taking 1 minus the overall order per unit time. 1 minus the overall order. Now remember, from this example, it was first order with respect to peroxide, first order with respect to iodide, 0 order with respect to hydrogen. Overall, it adds to 2. 1 minus the total order of 2. 1 minus 2 is negative 1. So you can hit that if you don't believe me. 1 minus 2, negative 1. Alrighty. That concentration unit will be set to the order of negative 1. Now remember, up here it was molarity. So it's molarity negative 1. And the time was minutes in this particular data table. It's going to be set over minutes, but generally you'll see that instead of writing it over 1, we'll just put it to the negative 1. So per molarity per minute is really molarity negative 1, minute negative 1. Let me repeat that. It's a way to solve for the K units. We used trial 1, plugged in the rate set equal to the concentrations raised to the orders with respect to each reactant, and solved for K. K is a constant. We could have used any of those 3 trials and it will come out the same number. To find the units of K, there's a formula. We start with 1, the integer 1, and subtract the overall order of the reaction. 1 minus 2 gave us negative 1. That concentration unit is molarity. Those little brackets stand for big M, molar units. So molarity negative 1, minute negative 1. That's the same as writing 1 over molarity times minute. But we'll see that written instead of as a fraction, but with the negative exponent. Pause here, take a look at the next example. Take a really close look at the data table and work to find a rate law. How does changing the concentration of A and B affect the rate? Are they first order? Are they second order? Work it out for a little bit and start the video again when ready.